So I'm sorry about the parking. This is scheduled the most difficult parking you can imagine. The rain and then the crack boil game at 5 o'clock. So I should warn you, when you leave, the parking is going to be even worse, but you just walk care because you'll be going in the other direction. So delighted to welcome you all here today and to introduce Peyman. Peyman's been in my group since 2008. He joined us in 2007 from Sharif University in Iran. And he's been a pretty tumultuous time for my group over the last few years, what with the rise of SDN and OpenSoil. But when Peyman joined the group, he came to me and said he had a pretty strong theory background, as many of our students do who come from the group, and said, I want to work on things that have an immediate practical value. And I want to be involved in something that has a mathematical basis and then a direct application to practice. And that's really where this topic came from that he's going to be talking about today. So it was, we were lucky, and it was a treat to him that he was able to identify something that had that characteristic. So I'm going to leave it to him. Before he starts, let me just tell you a little bit about how the rules work. I think there's a few people here who maybe haven't been to a Stanford defense before. Embedded in the room here are 5 examiners, and mostly sitting in front here. And the first roughly 1 hour is an open public session, and we ask that you, where possible, hold questions to the end, just to let Peyman make progress. Now, if you've got a burning question that you just cannot possibly move forward without knowing the answer to it, by all means ask. But generally, it's better if you leave it to the end. And then after some questions, we will ask you to leave, and then there'll be a closed session when we get to grow with Peyman after. David also here is the chair, so at that point he's going to take over and he'll be in charge. Please.
Thank you, Nick, for the introduction, and welcome everyone to this talk. So the topic of my thesis talk is scatter space analysis, which, as I will show you during the talk, is an abstraction model for covariant functionality of networking boxes that enable us to verify important properties about the network. It's not unusual to see news headlines like this almost every week in the news, that an outage in the network that we use every day causes some problems in our day-to-day activity. In this case, a Sprint network outage as a result of a fiber cut resulted in delay for Alaska Airlines passengers, or in the case of this other news, a level 3 outage as a result of a software bug in Juniper routers resulted in some major internet issues. Or even in the network that we use every day, we see examples like this. 2 months ago, we received this email on Gates building mailing list that says between 6:20 and 7, we experienced a complete network outage in the building when a loop was created by some staff members. And many examples like this that all shows that ensuring functional correctness of network is a complex task. In fact, even simple questions are hard to answer. Questions such as, can host A talk to host B? Or what are all packet headers from A that can reach to B? Or if A can talk to B, where the packets are dropped? Or what will happen if I remove an entry from a router? Or are 2 slices of network isolated from each other? Or are there any loops in my network? Or why my network is super slow? So we did a survey on Nanode mailing list about a few months ago, and we asked the network administrator to share with us some of their insight about operating and debugging network. In particular, one of the questions that we asked was to tell us about the most frequently seen problem in their networks. And among the 61 respondents, 57% of them said that the reachability issues that directly relate to the first 3 questions are among the top seen problems in their network. 53% indicated that latency, which is the answer to this last question, is one of the major issues. About 18% believe that security policy violation is a major issue, and 10% said forwarding. So you can see the problems that they face day to day is actually directly translated to answer these questions that I mentioned. But why is it hard to answer those questions? There are several reasons for that. One is that networks are getting larger, so we have to manage more ports and more switches. Network functionality is getting more complex. With over 6,000 RFCs that define today, it's not unusual to see some of these mechanisms and protocols that are listed here to be deployed in a network that we use every day. Also, debugging tools are really simple and rudimentary. In the same survey, when we asked the network admins to tell us about the tools that they use most often for network debugging, traceroute and MP are among the mostly used tools. But I believe the essence of the problem is the way that forwarding state is written in the networking boxes. So the forwarding state consists of a set of rules, forwarding rules, that are installed in the forwarding tables of switches, routers, and other boxes in the network that decide how an incoming packet is processed by the box and sent to the output nodes. So these forwarding entries or forwarding state is written into networking boxes through local instances of protocols running locally on a switch, by a remote instance of the same protocol running on all other boxes in the network, by local and remote instances of different protocols also running in the network, manually by different network administrators, and even by network administrators that left the company and no longer are. So as you can see, this forwarding state is not constructed in a way that lends itself well to verification and checking. And as a result, the best practice for debugging network is to probe these states by sending ping packets. But I believe if we can provide an abstraction for this forwarding state, then we can create tools that actually formally verify the network and operate the network correctly at all the time. And that's my thesis goal. So first, I want to define a simple and protocol-independent abstraction model for forwarding functionality of network. And then I want to use that to develop a set of solid, simple, and protocol-independent tools for analyzing, monitoring, and debugging the network. So the outline of my talk is as follows. I start by introducing this header space analysis framework, which is this abstraction model for forwarding functionality of network. Then I will use it to develop algorithms for finding reachability, detecting loop, and checking isolation of slices in the network. And then I will use this framework to develop some practical tools. I will talk about three tools. Hassle, which is an offline checking tool for control plane of network. NetPlanner, which is an online checking tool for the control plane of network. And ATPG, which is an online checking tool for data plane. And I will show runtime examples of these three tools on three networks: Internet 2, Stanford Backbone, and Google WAN network. So the bulk of this talk is based on a paper that was published in NSCI 2012. NetPlanner piece is based on a paper we submitted to NSCI 2013. And the ATPG part is based on a paper that will appear in Phoenix 2012 in a couple of weeks. So to get some insight of how we can abstract complexity in a complex system, let's look at other fields and see how they tackle similar problems. In particular, I want to look at the field of communication system because they have a kind of similar problem that they want to solve. So given a complex system that consists of many different components, frequency modulator, antenna, bandpass filter, and amplifier, and so on, we're interested to find out how a source signal is received at the destination. And the way that communication engineers solve this problem is first by finding the Fourier transform for this source signal. And by doing that, first of all, they find a simple representation of this source signal, regardless of the time characteristic of the signal. And second, they can abstract away the properties of this signal. So it doesn't matter whether the source signal is voice or data or video. They all have a simple representation here. And then they model each component in the system using its transfer function, which is, again, simple to use and also abstract away the complexity of all these components. So they all look like the same when they have the transfer functions. So inspired by this, I want to create this header space framework. And this is kind of the essence of what will follow throughout my talk. So the first step in building this framework is to model a packet based on its header bits as a point in a space that has L dimension. Each dimension is either 0 or 1, which we call the header space. So we look at the bits in the packet header as a flat sequence of zeros and ones. We don't care whether these 32 bits are IP source or IP destination. They're just zeros and ones, and we map each point to one dimension in that space. So based on that, this packet header will be this point in the space. I'm just showing three-dimensional because of obvious reason. Here, the L should be chosen long enough so that all the packet header bits that we really care about is contained within that L. So if you are analyzing a layer 3 network, then L will be all the way up to layer 3. If you have deep packet inspection middle boxes, then L will be the entire length of the packet. Also, a flow will be represented by a region because flow has some wildcard bits in it and corresponds to a set of points in that region. The second step in building this framework is to model all networking boxes as transformer of header space. Here I'm showing a simple packet forwarding element that has 3 ports here, and on each port I'm showing the header space for packets on that port. So we know that the behavior of this packet forwarding element can be represented by a set of rules, and each rule basically consists of a match and an action. The match telling us what are the packet headers that are affected by this rule, and the action tells us how those packets will be transformed to the output port. So the match corresponds to a region in the input header space, and the action basically tells us how that region is transformed to a region in the output header space. Also, if we have more rules in that box, we will have more of these match regions that are transformed to a region in the output. So when a packet comes, we find out which of those match regions the packet belongs to, and use the transformation to send the packet to an output port, and here the packet goes out from that box. So this shows that the behavior of this box can be modeled by a transfer function that accepts a header and port as the input. That's the header of the input packet and the input port that the packet is received on, and generate a set of headers and ports as the output. And the reason that we have a set at the output is that we want to be able to model broadcasting or multicasting, where one packet comes and many packets goes out of the box. So let's look at one example. If you want to model the forwarding behavior of an IPv4 router, all we need to do is to look at the forwarding table of that router. If this destination is sent on port 1, then we'll have a line in the transfer function that says send packets that has destination IP of h equal to this on port 1. And this destination IP of h is a simple way to refer to those 32 bits that correspond to the destination IP address, just happen to be the destination IP address. If we have more forwarding rules, we'll just add more lines in the transfer function. Then if you want to model the TTL decrement of this IPv4 router, we just add that action here in the action part. And even if you want to model the MAC rewriting part, we just add more action at the output. Let's look at some more realistic action to see how we can actually implement these actions. So for example, a rewrite action that's rewrite bit 0 to 2 with value 101 can be modeled by an AND that basically clear out these first 3 bits and then OR it with 101 to rewrite those values. Or an encapsulation action that encapsulate packet in a 1010 header should shift the header by 4 bits to the right and then OR it with 1010 to rewrite those bits at the beginning. Decapsulation is the opposite action, just shift to the left. A TTL decrement action looks at those 8 bits that correspond to the TTL. If they are 0, drops the packet. If it's more than 0, then reduce it by 1. And a load balancing action basically send the packet out on all the outgoing ports unmodified. And the reason that we send it to all these outgoing ports is that we want to explore all possible output paths. So one important property of transfer function is that we can compose them. And by composing transfer function, we can find end-to-end behavior of network. So over here, I'm showing a simple example consisting of 3 boxes. And I'm interested to see how the packet at the input of box R1 is propagated through the network. So I should apply the transfer function of box 1 and get the packet at the output. and then apply that output to the transfer function of box 2 and get the packet at the output of R2, so that the mathematical expression for this corresponds to the composition of these two transfer functions. And then if I want to go one hop further, I just keep applying these transfer functions to the result. So this shows that the behavior of this network from this input port to that output port can be represented by this black box that has this transfer function representation. The other property of transfer function is that we can invert them, and the inverse basically tells us all possible input packet headers that can generate an output packet header. I'm not going to give you specific examples of how to find the inverse, but I just intuitively show you what does it mean to invert the transfer function. If you have these regions in the input header space that are mapped by transfer function to those corresponding regions at the output header space of a box, then the inverse of transfer function effectively reverse these two and map from these output header spaces to the input header space. And because the transfer function itself wasn't a function, it was a map actually, it may be the case that one point here is mapped to 2 points at the output, and that's perfectly fine. The inverse of transfer function is also another map in strict mathematical terms. So the third step in building the header space framework is to develop a set algebra to work with header spaces. In particular, we want to be able to intersect, complement, and difference two regions within the header space and check subset and equality conditions on those regions. And the reason that we are interested in doing this set operation is that as you will see in the rest of the talk, at some point we want to check whether two slices of network are isolated or not, where at that point we need to intersect two of those regions. Or when we're checking whether a loop is infinite or not, we should check whether two regions of header space are subset of each other. So we need these operations in a way. And every region in the header space can be described by a union of wildcard expression. So we can reduce the problem to actually check these operations on the wildcard expression. So if we can do this set operation on wildcard expression, then we can subsequently do the same operations on header space regions. So I focus on that. And in the interest of time, I'm only going to explain how to do intersection of wildcard expression. The other operations are less used, but if you're interested, you can see the paper and see how we can go through that. So to do the intersection, we bit by bit intersect the two wildcard expressions using this wildcard expression intersection table. So all this table is telling us is that for each pair of bits, what is the common value that those pair of bits can take? So a 0 intersected a 0 will generate a 0 because that's the common bit value. 0 intersect with an x, that's a wildcard, will result in a 0 because wildcard will have 0 and 1 values. And a 0 intersect with a 1 will result in an empty because there is no intersection. So in this example, I'm intersecting 1, 0, x, x with 1, x, x, 0. I start from left to right. I intersect with 1 and get a 1 here. 0 with x, get a 0 here. And x with x, get an x here, and so on. So by doing this operation bit by bit, I can intersect wildcard expression. However, if I see only one z in the result, then the entire thing is empty. As an example, when intersecting these two wildcard expressions, I have a 1 and a 0 here, which result in a z. Therefore, the whole thing is empty. The reason is that these two wildcard expressions will lay in two different planes in the header space. So now that we have introduced header space analysis, let's try to use that to develop some useful algorithms for checking properties about the network. I want to talk about these algorithms. The first one is finding reachability in network. I want to find out whether host A can talk to host B, and if it can, what is the packet headers that A need to use for this communication to happen. So to do that, I start by injecting a hypothetical OLX test packet header from A into the network. This OLX test packet header is a packet that has wildcard on all its bit position, and it represents the set of entire possible packet headers that A can possibly generate. And I apply it into this virtual network. This is not the actual network. I take the one snapshot of the network, generate transfer function for all of these boxes, and then use those transfer functions to do the analysis. I don't actually inject any packets in the network. So I put this into the transfer function of box 1, which drop some part of those input regions and modify some parts, and we get some of those regions pass through the transfer function into the output. Then I apply the result to the next round of transfer function to see how it passed through that transfer function. And finally, I go through the last transfer function until I got to the destination. At this point, I solved the problem whether A can talk to B. It can, because some packet headers have reached all the way to the destination. And also, I find what the packet header will look like at the destination side. Each of the points within these regions correspond to a packet header that will be reached to the destination. The mathematical expression for these regions is done in a very interesting form. It corresponds to the union of two expressions. Each expression is the composition of transfer function along one of the paths that connect A to B. So we have one path that's going from 1 to 2 to 3 and 1 to 4 to 3. So we have two expressions here. And that's what we expect based on the composition of transfer function rule I discussed before. Similarly, if we want to find out what the packet header will look like at the source side, we find what they look like at the destination side, we can use the inverse transfer function technique to trace them back to the input. When we do that, we find out that these regions are the image of these regions at the input. The idea here is that not every point within this OLX packet header will survive all the way to B. Some of those points may get dropped along the way. Some of those points will go to other destinations. But these highlighted points are the set of points that will be mapped to here. If all the boxes have only forward action and don't modify the packet header, these two regions will look like the same at the source, but potentially we can have rewrite action and those regions change here. The next algorithm that I want to discuss is finding loops in a network. Again, the algorithm is very similar. We start by injecting an OLX test packet header from every switch port into this virtual network and follow the packet until it comes back to the injection port, at which point we find the loops. Very simple. So I'm running again a cartoon example here. I'm injecting this OLX packet header from this port into the box 1. I need to repeat the process for all other ports. So I'm doing it. The packet goes through transfer function of box 1, change shape. Then it goes through transfer function of box 2. Again, the shape is changing. Goes through transfer function of box 3. And for the sake of this example, it happened to be the case that actually something comes back to the injection port. So at this point, we say that, okay, we find the loop because there are some points here in this OLX packet that has gone through the loop and come back to the injection port. However, the problem is that are these points going to loop again in the next round or not? And to solve that problem, we need to use the inverse transfer function technique again. To basically trace this small region back to its origin and find out what part of that original OLX packet is actually generating it. So we call this orange region the original header space and the blue region the recurrent header space. The idea is that this original header space represents the entire set of packet headers that would come from this port, go through the loop, and then come back to this port again, because we started by injecting the OLX packet header. And the answer to this question, that whether the packets will loop again or not, depends on the situation of these two regions. If there was no intersection between these two regions, then the loop would be finite. Just consider any point within this original header space. It goes through the loop and map back to a point here, which is outside that region. And remember, this region represents the entire set of packet headers that would loop, so the next round of the loop won't happen. However, if this blue region was completely within the orange region, then the loop would be infinite. Again, taking any point within this orange region, after going through the loop, it's mapped back to a point in the blue region, which is again inside the orange region, so it can loop again in the next round as well. And if you have a partial intersection like this, we need to do more work to figure out whether the loop is finite or infinite. The idea here is that these points in the blue region that are outside the orange region, they fall within this first category. So we can just focus on the intersection of these two regions, this smaller cube here. And for that, we can use the inverse transfer function again to find out what part of that original orange region was generating this smaller region. And when we do that, we find that, okay, this is the region, so if the problem reduced to the first case, and we know that the loop is not infinite. However, if we end up in the same scenario again, we just keep repeating and repeating again, and every time we repeat this process, the regions start shrinking and shrinking until they may end up being in one of the first two cases or reduced to empty. The case of loops that are taken care of by TTL decrement fall within that third category. So the last check that we want to develop here is checking isolation of slices. But first we need to define what do we mean by a slice in the network. So a slice is defined by three things. A topology consisting of a set of switches and routers that belong to that slice, and a set of predicates on packet headers that is controlled by that slice. So if we have a network like this, and we want to create a VLAN slice on these three boxes, the definition of that VLAN slice will look like this, where these correspond to the predicates for a VLAN slice, which is VLAN equal to A on the packet headers. This corresponds to a region in the header space that defines that predicate. And because the VLAN is stretched across these three boxes, we have one of these cubes on each of these switches. But why do we care about isolation of slices? There are many applications for that. I just mentioned a couple of them here. For example, in the case of banks, they may need it for added security in their networks. Or a healthcare network may need it to comply with HIPAA, which requires that healthcare doesn't share patient records with each other. Now back to the original question, how can we check if two slices are isolated or not? Imagine we have another slice defined on the same network. The first thing that we need to check is that the slice definition don't intersect. And we can use the intersection operation from the header space to make sure that these regions don't intersect, which is the case for this example here. The other check that we need to do is to make sure that packets don't leak from one slice to the other, because it may be the case that a packet on VLAN A is rewritten by VLAN forwarding to VLAN B and lead to the VLAN B slice. And to check for that, we need to apply the header space definition of each slice to the network transfer function and find the image of that slice under network transformation. So I'm doing it for the blue slice here, and I find that the image of this blue slice under network transformation is these dashed region. This shows how all the possible packets that belong to the blue slice will be forwarded after one hop of forwarding. So we see over here that the packets that belong to the blue slice on these spots can be forwarded to the next hop into points in this region and has some intersection with the red slice. So we say that packets can actually leak in this example. Before moving on, let's recap what header space frameworks do for us. It's a simple, as I showed you, it's a simple abstraction that gives us a common model for all the packets that can traverse in the network through the header space notion. A common model for forwarding behavior of all networking boxes through transfer function notion. And a mathematical foundation upon which we can check properties through the network, and that's through the notion of transfer function, its inverse, and a set of set operations on header spaces. So now let's see what kind of tools we can create using this framework. And I want to start by introducing Hassel, which is a Stanford header space library, and it's an implementation of this header space framework. There are two versions of Hassel, one in Python and one in C. The code consists of a foundation layer that implements header space and transfer function object. And then there's an application layer that uses this foundation layer to do the reachability, loop detection, and slice isolation checks. And the interesting observation here is that all of these checks, less than 100 lines of code in both of the implementation. The idea here is that the foundation layer gives such a powerful abstraction that we can easily implement checks on top of it. Yes.
So a lot of what you've talked about hinges on being able to find these inverses efficiently. So is that at all an issue, or is it?
No, there's no issue for
Is
this.
that straightforward?
I just don't show the implementation in the interest of time. Yeah, it's easy to find. It's conceptually just reversing the input and output. So the hassle also comes with the parser that's only implemented in Python. The parser basically can parse the CLI output from Cisco IOS, Juniper Junos, and OpenFlow table dump and generate transfer functions from them. For example, in the case of Cisco IOS, it can read the IP table, ARP table, MAC table, spanning tree output, and config files, and compile them down to transfer functions that then we can use in our analysis. And it also keeps track of which transfer function rule is based on which lines in the CLI output. So in case of problems, we can trace it back to the actual configuration in the process. And the code is also available at this URL if you're interested to see. So we tested Hassle on Stanford Backbone Network. It's the network that's connecting all the departments and dorms together. As a little bit of background, Stanford owns 6-16 IP domain, and overall, all of these boxes have 750K IP forwarding rule, about 1.5K ACL rules. About 100 VLANs are defined in this network, and VLAN forwarding is also enabled on these boxes. So we ran a loop detection test here, and to do that, I got a complete snapshot of the network configuration through one of the admins, Johan. I fed those configuration into the Hassle parser to generate the transfer function, and then used it to run the loop detection test. Here I'm showing you one example of problem we find. This shows the spanning tree for red VLAN, and this part shows the spanning tree for a blue VLAN on the network. And I find that the packet on red VLAN can get broadcasted on the VLAN, go all the way to the core router, but the core router rewrite the VLAN ID to the blue when it comes back to that router down here. The VLAN is again rewritten to red, and then it gets broadcasted on the red VLAN again and again. So the packet basically goes from red to the blue VLAN back and forth. And spanning tree, which is a protocol that's designed to make networks loop-free, is actually causing a loop by inappropriate interaction of two instances. Just a small note on performance of this tool on Stanford network. So generating transfer functions using, I only use a laptop that has a single quad-core CPU and 4 GB of RAM. On that, generating transfer function takes about 150 seconds to complete, and completing a pairwise reachability on average takes 40 milliseconds with a mean of 1 and max of 500 milliseconds. And the loop detection test on 30 cores take about 2 seconds to complete. And that's based on the Hassle implementation and with multi-threading. Just a small note of how these things scale. So the scalability of reachability algorithm is dr squared, and loop detection is pdr squared, where d is the diameter of the network, the maximum number of hops that packets can traverse in the network. R is the maximum number of rules in a switch, and P is the number of ports that you inject the packet from in the case of loop detection algorithm. So if tomorrow Stanford decides to acquire 3 more campuses and build a network and connect them using this structure, then the Hassle toolcat will still run in this network. Reachability will increase to 100 milliseconds and loop to 20 seconds. And if further Stanford double the number of rules that exist in this network, then the performance will be something like this: less than half a millisecond for less than half a second for reachability and 80 seconds for loop detection. So Hassle is a good tool for offline static checking analysis. However, it takes several seconds to collect all the states, parse them, generate transfer function, and then run the test. The next challenge is how to make it real time. So as the churn is happening in the network, we want to be able to verify that, okay, the policies, the design policy of network has been satisfied. And one solution for that is to rerun the analysis every time the network changes. However, there are several drawbacks for that. One is that collecting all the state from all these boxes is slow and wasteful. It takes a lot of resources just to read that data out of the boxes. The other problem is that redoing all this computation is kind of inefficient. When only a small change happens in the network, you could potentially use some of the computation that you have done just to update the results. And that's the motivation for the next tool I'm going to introduce, which is called NetGlommer. So as I mentioned, there are two challenges. The first one is collecting the forwarding states, and the other one is updating the check results in real time. Software-defined networks provide a nice way to check for that first property. If you look at the interface between the controller and the switches, it's a logically centralized location to observe all the state changes that happen in the network. We can see all the installation of rules, removal of rules, or link up, link down events that happen just by tapping into that communication. And so for the rest of this talk, I assume I have access to a stream of state changes that happen in the network, and I focus on this second challenge, which is updating the check results in real time. So the system that I built is called NetGlommer. It's a system that sits between the controller and the switches, and listen to that communication and try to verify every state changes with network policies. But before we proceed, I need to make a point here that most policy and invariance can be expressed in terms of reachability. As you see in my talk, loop freedom is reachability plus some extra stuff. And most other policies like checking black holes or isolation of hosts or making sure that some communication is happening via middle hops or maximum hop count in the network, all can be described by some variety of reachability analysis. So I really focus on computing reachability incrementally and really fast, and the key idea to do that is to reduce computation as much as possible. So the system that I built is called NetGlommer. It creates a virtual dependency graph of all the rules that exist in the network and use it to compute reachability. In that graph, nodes are corresponding to forwarding rules in the network, and directed edges correspond to next hop dependency of rules. Meaning that I say there's a directed edge from rule R1 to R2. If in the physical network there's a physical link from switch 1 to switch 2, and also the output header space of R1 has some intersection with input header space of R2. Basically what it's saying is that there exists at least one packet that can be processed by rule R1 and then followed into rule R2. So to understand how NetGlommer works, let's run through one example. Imagine you have a simple network consisting of these 4 switches. I look at the forwarding table of each of those switches, and for each rule, I put a node in the NetGlommer graph, which I call the timing network or timing graph. And then I need to create directed edges between these nodes in the graph. I use that intuition. Here there is a directed edge from this top blue to the top green node because there is a link here, and the output header space of this has some intersection with the input header space of this. Similarly, if I look at all other nodes in the network, I can create these other directed edges and create this graph. Also, each rule in the NetGlommer keep track of all the higher priority rules within the same table whose input header space has some intersection with itself. So the idea here is that the higher priority rules have precedence in processing packets that will otherwise match on the lower priority rules. So we need to keep track of that, and you will see how we use that in next slides. Now we can use this structure to compute reachability. Let's say we want to compute reachability from A to B. All we need to do is to connect a source node in the place of node A here, and a probe node in the place of node B. The job of source node is to inject flow into this virtual graph of NetGlommer. Again, I want to mention that we are not sending any packets in the network. This is a virtual instance of the network, and we just use it for computational purposes. So these OX packets will go through those boxes and get transformed by the rules and just get propagated through the network. You observe that these regions only transfer along these directed edges that show how the packet can go from one rule to the other. And as these packets are traversing, they also keep a pointer from the next flow to from each flow to the next flow to see the history of flows as it travels through the net-plumber graph. Now, the computing reachability was something that we could have done before. The real power of net-plumber is to update reachability results in real time. So imagine I add a new rule here to this green box. First, I need to create these directed edges to connect this new rule to the other part of the net-plumber graph. I also need to create these inter-table influences of rules, because there is one here. And now we can get the flow from this box, process it through the green rule up to here, and then send this back to the network and all the way to the problem. And at that point, we have done part of the update. The other part is that there is a link, there is an intertable dependency link between these two green rules. And as you can see, the packet that match on 100x will now match on, that were previously matching on this second rule will now match on this first rule because it's in higher priority. So we need to update these flows that's flowing through this down path here. And to update that, they probably reduce because they are no longer matching on those paths. So it reduces like this. And at that point, we have the updated reachability result. So the real power of probe node is not just getting flows at some point in the network. They can actually check policy on those flows. So for example, if you wanted to check this policy that says packets with header 1001 to server should pass through the green box, probe node can check that policy because it has access to all the flows here, and it can use these history links to trace it back and see, okay, the 1001 header is actually coming from this path that's passing through the green box, and the policy is actually verified in this case. Imagine at some point somebody decided to remove that rule on top of blue box. Again, net-plumber can easily update the result by first removing the flow that's going through this path. The blue rule was part of that path. And also because there is an intertable dependency here, those packets that were previously going through this blue rule will now go through this bottom path, and they will go through this route. So we need to update these flows and add those to this bottom path. And now we can remove these safely from the net-plumber graph. But at that point, the policy is violated and the probe node gets angry at us. Okay. Now let's look at a couple of examples to see how we can do more complicated policy checking with net-plumber. So imagine we have a graph like this, whose plumbing network is this complex graph. It's obviously much more complex than the actual network because nodes here corresponds to root in the actual network. Now imagine we want to check the policy that guest cannot access server S, and we have two guests here and a server here. To check this policy, we connect two source nodes in the place of these two guests here. So this corresponds to this corresponds to this. And I connect the probe node in the place of server. And I program the server to look at all the flows that it's receiving and making sure that none of those are actually coming from these two sources. Or even a more complex policy that says HTTP and HTTPS traffic from server S to client C doesn't share the same path. All I need to do for that is to connect again two source nodes in the place of this server, one generating HTTP and one generating HTTPS traffic, and have a probe node here that makes sure that the HTTP and HTTPS traffic that it's receiving are not coming from the same path. That's equivalent to checking the policy. The other question is that how can we distribute net-plumber to improve its performance and scale to larger network, and if it's possible? The answer is that yes, we can do that, and the idea for doing that is by slicing network based on forwarding equivalent classes. So if you look at a typical net-plumber graph, it will look like this. There are clusters of highly connected rules, and there are some rules that are violating this perfect clustering condition. So you can imagine in the case of an IPv4 router, These corresponds to rules that are processing one subnet. This corresponds to rules that are processing another subnet. There are some default or aggregate rules that are interacting with both of these, basically processing packets that belong to both of these. So the way that we can distribute the load is by chopping off this network along these cluster boundaries and assign each smaller netplumber graph to one instance, and that can be run independently from the other instances and probably faster. And those rules that are violating the clustering condition should be replicated on both of the instances. And then basically the final result is the aggregation of the results that are observed by this probe node at this cluster. If a violation happens in any of these clusters, then that's a violation for the network. So I implemented netplumber in C++. It uses the foundation layer of Haskell C as its base. And the structure basically looks like this. There's a netplumber manager layer that's basically creating the netplumber graph and managing the rule node, probe node, and source nodes. And it provides an API for adding or removing a rule in the netplumber graph, an API for adding and removing links in the netplumber graph. And you can imagine these two API are useful to update netplumber as changes happen in the network. There is an API for adding, removing source node, and adding and removing probe node. We can use them to implement new policies in the netplumber. And this API also enables us to program the probe node to check for the policy that we actually want, and also set a callback function in this probe node so that when a policy violation happens, that callback function is called and we can respond to that violation. And also there is a callback function for loops that happen in the network that we can set through this API. So I experimented with netplumber on Google WAN network. This is the topology of Google WAN. It's a network that's connecting the data centers of Google across the world, and it's the largest deployed SDN that's 100% open flow. And the data center is effectively handing off of these switches at the edge. And overall, there are 160K open flow rules that are installed in this network. So the policy that I checked on Google WAN is to make sure that all 52 edge switches can talk to each other. That corresponds to communication between all the data centers that Google owns. This translates to about 2,500 pairwise reachability check. And to do that, in the equivalent netplumber graph, I connect the source node and the probe node to each of these edge switches, program the source node to send all its packets into the netplumber graph, and the probe node to receive those packets and make sure that it's receiving packets from, basically receiving flows from all other source nodes. I used two snapshots of the network that are taken 6 weeks apart. The administrator for this network gave me a complete dump of the open flow rules. And I used a parser to basically parse them into a transfer function of it and node. I used the first snapshot to create the initial netplumber state. So netplumber should be initialized by all the rules that already exist in the network, which takes about 34 seconds. And then I used the diff of the two snapshots as sequential update that I feed into netplumber. And I measured the update time for each of those changes that happened in the network. This graph shows the runtime. The x-axis is runtime in milliseconds, it's a log axis, and the y-axis is the CDF of runtime. It shows that for 60% of rule with only a single instance of netplumber, it takes less than 1 millisecond to update this huge policy check. And about 95% of rule will be checked in less than 10 milliseconds. These rules that takes much longer are the default or aggregate rules in the network, because adding or removing them in the netplumber requires a lot of changes, a lot of directed edges should be created and flows should be routed and so on. However, if you wanted to do the same check using Haskell, meaning that get a complete snapshot, process it, and fit it into Haskell and so on, it will be a point further down here, more than 100 seconds to complete. Another interesting observation is the way that adding more instances or clustering netplumber will work. this table shows how the runtime, the mean and median of runtime is changing after we go from 1 instance up to 8 instances. And as you can see, after 5 instances, we are not really getting much more benefit. The reason for that is that you remember that the net plumber graph, there was clusters. And if we actually do the clustering on those actual cluster boundaries, then we get most of the benefit. Going beyond that, we are essentially replicating all the rules across all the clusters. So the 2 clusters that will be result from this will not have any more, any less rules, and so the runtime will be effectively the same. As another benchmarking experiment, I ran a similar reachability check, but I just did one pair of that to see how one pair will react on different networks. I repeat the same process on Stanford and Internet 2. As you can see, the average pair rule update time is well less than 1 millisecond on all of these networks. For the case of Internet 2, it's a little bit higher because there are much more rules in each of those processes. So, NetPlumber and Hassel both designed to find problems in the control plane. However, what will happen if a switch or link goes down, or a link is congested, or an ASIC or hardware is broken? There's no way that such tools can detect that. The only way to detect this sort of data plane problem is at the runtime of the network through either active testing or passive monitoring that packets that are actually running in the network. And that's the motivation for this last tool, which is called ATPG. So the ATPG, or Automatic Test Packet Generation Framework, has this scope. We want to monitor the data plane by sending test packets in the network to achieve maximum rule coverage. Just in the same way that a good software test suite will try to exercise every rule in the software program by at least one of those test suites, in the same way we try to send at least one test packet that exercises each of those rules. And we want to achieve the minimum number of such test packets in the network. And we also want to be able to handle constraint on the terminal ports from which we can send packets in the network, and also constraint on the headers of those test packets that we use in the network, because we may not be able to send any packet that we want for obvious reasons. And once an error is detected, we want to be able to localize that error. So I just tell you about the algorithm sketch of ATPG here. If you're interested, you can refer to the paper. So the algorithm is as follows. We start by using HSA to find reachability between all the terminals that we have, between all pair of those terminals, and in the process we find all the forwarding equivalent classes. Then we pick a sample test packet for each forwarding equivalent class, and then use a mean set cover algorithm to choose a set of those sample test packets whose rule coverage corresponds to the entire set of rules in the network. As I mentioned, you can refer to this paper if you're interested in details. But how many packets is needed for doing such coverage? The idea here is that the number of packets scales roughly with the number of forwarding equivalent classes in the network, which is proportional to the number of unique subnets that we care about in the network. So in the case of Stanford backbone network with 16 routers, 4,000 packets was enough. In the case of Internet 2 with 9 routers, 30,000 packets was enough. And even if you wanted to test all the rules 10 times per second, this requires less than 1% of link bandwidth. We had a small implementation of ATPG on Gates, Packard, and CIS network that constantly sending test packets here. And coincidentally, at the time that we received this email that says network was down as a result of the loop, we were running actually ATPG. And this is the number of failures per minute over time. You can see around 6:20 to 7 it peaks the number of failures per minute peak here. And we can use ATPG to actually localize the affected area and find where the problem is happening. Before I finish my talk, I want to zoom out a little bit to show you the bigger picture. As a network admin, I have a set of policies that I want to implement in my network. And that's the job of the control plane logic to translate those rules, those policies into rules that are getting installed in the switches or routers. That's the forwarding state of the network. The job of header space analysis to model this forwarding behavior based on these rules. And then Hassel and Nettlomer try to verify equivalence of policies and these rules based on this view that header space analysis is providing to it. And ATPG try to verify the actual data plane behavior by generating test packets based on this view that header space analysis provides. So the whole framework provides coverage for both the control plane and data. Before I conclude, I want to mention some of the related works here, because little bits and pieces of HSA can be found in the literature. So in the geometric packet classification works, you can see that the ideas of geometric representation for packet headers. But the main difference with HSA is that they use protocol fields as axes or dimensions of the space versus HSA that uses each bit as a dimension that allows it to be protocol agnostic. The axiomatic basic of communication in SIGCOMM 2007 it also have an equivalent definition for packets and packet forwarding in the network. However, they didn't, because the goal was to verify protocols and not network debugging, they didn't provide any algorithms for network debugging or any tools for that. These two other papers actually present some algorithms for finding reachability, but again, the algorithms are protocol dependent. They are for IPv4. And also, it's just for reachability. They don't give any insight into how to build other checks and so on. Finally, there's one more. The Amphitheater system in SIGCOMM 2011 has similar goals as Hassel to do some checks on the network. However, again, this is protocol dependent. And also, it's about 2 to 3 order of magnitude slower than the C-based implementation of Hassel. It uses SAT equations to verify properties about the network. And as it uses SAT solver, it can only give one example or counterexample when a failure happened in the network, versus HSA that can give all the example and counterexamples. And finally, Veriflow has similar goals as Nettlomer. However, again, this is protocol dependent, and further, it can only handle IP destination rule. And it can only also handle a forwarding rule versus HSA that can do any type of rule and also any type of action. So header space analysis over all of this has disadvantages. The first solution that's protocol independent, fast and practical, and can be used as basis for building many more tools. There are also a lot of complementary work that is required along with HSA to create this ecosystem for network debugging. Just list some of those works here, and if you're interested, you can refer to them. So I want to summarize my talk at this point. I started by introducing header space analysis as a simple abstraction model for forwarding functionality of all networking boxes that gives us a common model for all packets, a common model for forwarding functionality of all boxes, and a mathematical foundation upon which we can create algorithms for checking them. I use HSA to develop algorithms for finding reachability, detecting loop, and checking isolation of slices. I use it to develop a tool for real-time policy checking, and another tool for automatically generating test packets to achieve maximum coverage with minimum number of test paths. I showed how a solid theoretical foundation on the way that forwarding functionality of network works can lead to practical implementation that change the way that we design and operate networks. Before I finish, I want to thank a few people here. I want to start by thanking David Dill for agreeing to be the chair of my committee. David, I'm also thankful to you for all the helps you did for me to understand the formal verification stuff and try it on networking. I want to thank Scott, who agreed to be on the committee in the last minute call and driving all the way from Berkeley in this rain. Also, sorry, Scott, that we didn't have any chocolate.
I live in Palo Alto, so you have a lot less to thank me
for. thank Sachin for being on my committee. Sachin, unfortunately, we didn't have a chance to collaborate closely, but I'm looking forward to future opportunities for that. I also want to thank Guru. Guru, during the past 5 years, I enjoyed all of our talks and communication with each other. I learned a lot from you, and I really appreciate that. I also want to thank Balaji for agreeing to be on my committee. Balaji, I'm also thankful to you for all the things that I learned from you through the classes and interaction with the students in your group. Also, thank you for being in the reading committee. I know your time is really valuable and I appreciate it a lot. I also want to thank George Ragas, who couldn't unfortunately come here today. But a lot of work that you see today is not possible without his help. He's this really energetic and fun guy that always gives you ideas, inspiration, at the same time criticism for your work, and I'm really thankful to him. I also want to thank my advisor, Nick, who graduated. 6 years ago, when I was interviewing at US Embassy to get my visa and come here, the officer asked me, who will be your potential advisor? I only give one name, Nick McKeown. Nick, I'm thankful for giving me the chance to work with you during the past 6 years and providing a really great PhD experience for me that's far beyond what I could imagine and wish for. Nick, I think for me and for many people in the group, you're a true friend and an inspirational figure. I also want to thank my co-authors, James and Michael, for their help with the ATPG and NetPlumber work. My mentors at Google and Ericsson, Scott White and James Kemp, and all the students in the group, all the students, postdocs, and visitors in the group. I learned from each of you during my PhD, and all your feedback and comments made my papers and talks look much better. I also want to thank Persian Student Association at Stanford, who some of the people are actually coming here. Without you guys, it wouldn't be the same, my experience at Stanford away from home. I also want to thank my parents and my brother for all the help and support during these years. And last but not least, I want to thank my wife, Roya. If I want to summarize my life in the past 6 years, this would be a great summary. Stanford in the background and here at the front. So I want to thank you for all the love and care you gave me during these years. And finally, I want to thank you all for coming to my